All right, so let's talk about the chain rule. So this is going to be a really super important section, really for the rest of the semester. It's just a really important way to be able to take derivatives. So one thing I just put in here is just recall if you're given this function g of x, and I'm going to write this on a separate piece of paper. If you're given two functions, let's say one is g of x is equal to 4 plus 3x, and then you're given another function f of x. Just a little notation. If we have a composite function, this means f composed with g. We're taking a composite of those two functions of x. This notation is the same thing as saying f of g of x. So what that means is that g of x is going to be the input. G of x is going to be the input. And we're going to take g of x and we're going to put it into the function called f. So we're taking g of x, which is 4 plus 3x. We're taking this and we're inputting it into the function f everywhere we see an x. So this is equal to the square root of 4 plus 3x. Okay. So we're going to be doing kind of composition of functions in this section and looking at inside functions and outside functions. So when you look at this function, you see an inside function in the 4 plus 3x, and then that's going to be the inside. And then you see an outside function, which is that square root function. So I just wanted to show you that this square root of 4 plus 3x is really composed of two different functions. It's composed of 4 plus 3x on the inside and square root of x on the outside. Does that make sense? You see that? So important concept in this section. So if we want to find the derivative of that same function, what we're going to do is identify the inside function and the outside function. So like I just explained, the inside function is 4 plus 3x. But now we're just going to give it a certain name. We're going to call the inside function u. We're going to give it a name u. And we're going to write the inside function with the variable x. Outside function now is going to be the square root of u. We're not going to call it the square root of x. We're going to call it the square root of that function u, which makes sense because it's the square root of 4 plus 3x. And then we're going to give the outside function the name y. Now we're going to look at the derivatives of each one of these. So we're going to take the derivative dy du, so that means our function called y right here. Our function called y, we're going to take the derivative of square root of u. So we've done square root function before where we've found that, but this is one that comes up frequently. So the derivative of the square root of u is 1 over 2 root u. And then if we take the derivative of the function u, this 4 plus 3x, that derivative is going to be 3. All right, then let's find the derivative of that. So let me get another sheet here. So what we have so far, let me just write this. U is equal to 4 plus 3x, and we're saying that y is equal to the square root of u. And then du, the derivative of u with respect to x is 3. The derivative of y with respect to u is going to be 1 over 2 root u. So derivatives that we already know how to do. Now what we're going to do is we're going to combine these things. We're going to write this as dy dx. Because ultimately what we're trying to do is find the derivative of y. We want to find the derivative of this with respect to x. And we don't know how to do that right now. We don't have the tools. It's not a product of something and it's not a quotient of something. So we don't know how to find that derivative yet. So we need the chain rule to do that. So we want to find dy dx. The way that we're going to find it is by using these two parts. We're going to find the derivative of u with respect to x. And we're going to multiply that by the derivative of y with respect to u. And this should be du, dy du. I just had a u there. It should be du. And we're sort of going to think about these du's canceling. We're not really canceling them, but it's one way to look at this and kind of remember how to do the problem. They sort of look like they're going to cancel, and we're going to be left with dy du, but they don't really cancel. All right, so let's fill those parts in. Du dx is 3. And dy du is 1 over 2 root u. So we're just multiplying the du dx by the dy du. But we can't leave that as our answer because that's in terms of u, and our answer has to be in terms of x. So we're going to take this u, and instead of u, we're going to go back to 4 plus 3x. So this is going to be 3 is in the numerator, 2 is in the denominator, and it's 2 times the square root of 4 plus 3x. So that's going to be the derivative using the chain rule for square root of 4 plus 3x. All right, any question on that?
Is it 3 over 2 times?
Yeah, it's 3 over 2 times root 4 plus 3x. So that whole thing, 3 is over that whole denominator. That's the derivative of this function. So something that we didn't know how to do previously. We didn't have any rule that let us take that derivative. But now we have the chain rule. We can do that. All right, let's look at another example. Yeah. So let's look at another example here. So on your sheet. So let's find the derivative of y is equal to 3 plus 2x squared. So again, the way that I have this written is it's a composite function. Again, it has an inside function and it has an outside function. So let me write that on a separate sheet here. So y is equal to 3 plus 2x squared. So we're going to call our inside function u. So looking at this function, what is the inside function? So 3 plus 2x is the function that's inside. That's going to be our inside function. So 3 plus 2x. The outside function, we're going to call that y. So this is inside, and then y is going to be the outside function. What's the outside function? It's going to be u squared. We're taking this u, 3 plus 2x, and we're squaring it. So the outside function is something that's being squared. The thing that's being squared is u. So u is going to be the outside function. And then we're going to take the derivative of each one of those pieces and then put those pieces together. We're going to find du dx and dy du. Okay. So now let's take the derivatives. So du dx. That means we're going to find the function called u and take the derivative of that function with respect to x. And what is that going to be equal to? It's just going to be 2 because we're taking the derivative of 2x. Derivative of 2x is just 2. So du dx, derivative of u with respect to x is 2. All right, then let's take the derivative of y with respect to u. So, I wrote it in a different order than what's on your sheet. So dy du, derivative of y with respect to u. So looking at this function y.
Does that mean we got to factor it? Like, we have a 1.3 plus 2x and then...
No, just looking at u as being a variable. So if I had the function, like if I just had y is equal to x squared and I said, what's the derivative of this function y, what would you tell me? 2x, right? You bring that exponent down to the front on those power functions. So the same thing here. The variable is u. So 2u. So just like this one is 2x, this one is going to be 2u. Okay, so just take the derivative in the normal way. All right, so we got the inside function, outside function, and then we're going to put those things together. So we have dy dx. And so you have this on your sheet. It says that's going to be dy du times du dx. And this is going to work. It looks like those du's cancel. We're not going to really cancel them. But first of all, we're going to write in, just copy dy du. What's dy du? 2u. and then we're going to write du dx, and that's going to be 2. So it's going to be 2u times u, which of course is 4u. But we can't leave our answer in terms of u, it has to be in terms of x because we're finding dy dx. X has to be the variable. So this is going to be 4 times. So we have to write in u. What's u? 3 plus 2x. U is 3 plus 2x. So 4 times 3 plus 2x. And you can leave it factored like that. You don't have to distribute it. You could. It's fine. But that's the final answer. That's the derivative of 3 plus 2x squared. Four times this, like you could just distribute the 4. It wouldn't matter. But normally I say leave it factored. But either way would be fine. All right, any question on that? All right, let's, why don't you try the next problem on the sheet where I'm asking you to find the derivative of that cube root of 1 plus 4x. So give that one a try. So I kind of gave you a head start here just to find the inside function and the outside function, take each one of those derivatives, and then combine it together. All right, let's take a look at what you have for this problem. So inside function, 1 plus 4x. The outside function is that cube root. So we're looking at a cube root of something. So the thing that we're taking the cube root of is u. So the outside function y should be the cube root of u. And then you can write the cube root of u as u to the 1/3. It's easier to take the derivative if you write it that way. All right, so let's take the derivative of each one of them. Du dx, derivative of u with respect to x is 4. dy du, derivative of y with respect to u. So 1/3 u to the negative 2/3. Yeah, so bring the exponent down to the front, u, and then you subtract 1 from 1/3. So 1/3 minus 3/3 is negative 2/3. All right, then we're going to combine everything. Dy dx is dy du. So dy du is 1/3 u to the negative 2/3. So just copy what we have up above. Times du dx times 4. And this is all being multiplied. So we have this 1/3 times this 4. So that's 4/3. And then instead of writing u to the negative 2/3, I want it in terms of x. So what do I write instead of u? Yeah, I take this 1 plus 4x and put it in there instead of that u. So 1 plus 4x to the negative 2/3 power. So that's what you should have gotten for an answer. 4/3 times 1 plus 4x to the negative 2/3 power. And then normally, if we can get rid of those negative exponents, we can try to get rid of those negative exponents. So that means that this thing is going to be put down to the bottom, 1 plus 4x. So we have 1 plus 4x to the positive 2/3 power. And it's just good to practice moving those negative exponents around.
So do you want it like that?
Yes. So when it's practical, when it makes sense, unless it makes things look horrible, try to get rid of the negative exponents.
So if we wanted, we could do like in the beginning, it'd be like 1 over 3u and then 2, and then power to 2/3 like in the beginning.
Yes. Yeah. Yeah, you could have changed the negative exponent here and written this as 1 over 3u to the 2/3 power. Yeah, that's totally fine. Because it looks a little better when you don't have that negative exponent in there. All right.
You could just commit to memory that if anything is to the something third power, that it's the same as 1 over
You mean like if you have something to the 1/3 power, like u to the 1/3,
Yeah,
and you're taking a derivative of it? Is that what you mean?
yeah.
Yeah, it's going to be just like when we had u to the 1/2, it was 1/2 x to the 1/2, and 1/3 is going to be 1/3 u to the 2/3 power. So similar to when we had x to the 1/2, square root of x. All right, any other questions?
Just one thing I forgot about. So u was like to the power 2/4. That would be like if you're gonna convert it to what u over 1/3 is 1/3 will be like 2/3. Like if in the square root there was a u to the second power.
Instead of a square root, like inside?
Inside, yeah. Would that be u 2/3?
Yeah, that's the same thing as u to the 2/3 power. So the denominator is the index and the numerator is the power. Yeah. So you would be taking the square root of that.
What about negative? It was -2.
If it was a negative there, y would be the cube root of 1/u squared. And then then it doesn't, well, then it would be the same thing, I guess, as it would be u to the, if we write negative 2/3, be the cube root, yeah, then it would be u to the negative 2/3 power. All right, anything else? All right, let's go back to your sheet then, and now let's find this derivative, the derivative of y is equal to the sine of the cotangent of x. So what's different about this problem? Or what's weird about this problem compared to what we were doing in the last section? Yeah. So it's not the sine of x times the cotangent of x. Okay, this is something different. So this is not y is equal to the sine of x times the cotangent of x. If we were taking, do we know how to find this derivative already? Sine of x times the cotangent of x? Do we know how to find this derivative? We do. We already know how to find this derivative. Because what would we use? Product rule. This would be the first times the derivative of the cotangent. So it would be the sine of x times the derivative of the cotangent plus the cotangent times the derivative of the sine. We already know how to do that, right? Product rule. That's not this. This is not sine of x times cotangent of x. Did we know how to do this? Can we use the product rule on this? You can't, because you can't multiply sine times something else. It doesn't make sense. Sine is an operation. It means that we're taking the sine of the cotangent of x. Just like if we would write y is equal to the square root of x, that the square root is an operation. You have to take the square root of something. It tells us what to do. The square root is the outside function, and the x is the inside function. Just the same here. Sine is going to be the outside function, and cotangent is going to be the inside function. We're going to take the sine of the cotangent. All right, do you see the difference?
So the cot x is the angle.
Yeah, x is, whenever you take a trigonometric function of something, the something is always the angle. All right, so let's set this up the same way that we did those other ones. Let's find the inside, u. Yeah, u is going to be the cotangent of x, and y, our outside function, sine of u. Now let's find our derivatives. Du dx, derivative of cotangent of x. So negative cosecant squared of x has to be in terms of x. And here we're finding dy du. U is our variable here. Derivative of sine of u is cosine of u. So u is our variable. So if we're saying we're finding the derivative with respect to x, x has to be our variable. With respect to u has to be our variable. All right, let's put them together. So dy dx, that's what we ultimately want to get. We're going to get that by multiplying these two things, du dx times dy du. So we have negative cosecant squared of x times cosine of u. So we just multiplied those two things that we found the derivative of. And then we have to do what? So negative cosecant squared of x times the cosine of times the cosine of u. Instead of u, I'm going to write cotangent of x. So instead of u, I'm going to write cotangent. So this is the cosine of the cotangent. It's not the cosine of x times the cotangent. It's the cosine of the cotangent of x. There's no x after that cosine. So this is a product of two things. It's a product of this negative cosecant, and it's the product of the cosine of the cotangent of x. So there's nothing you can do. They can't distribute anything. There's no pluses or minus in there. It's just this thing multiplied by this thing. So we'll just leave it like that. And if you put the cosine of the cotangent first, it doesn't matter. All right, question on that?
Is this your formula sheet for the test?
Probably.
Probably. Okay. Double check.
All right, let's look at the next page. And here's a theorem that talks about definition of a chain rule. So in Leibniz's notation, so Leibniz was a mathematician, and the notation that we've been doing so far is Leibniz notation, where dy dx is equal to dy du times du dx. So now we're going to learn another notation, and you'll be happy to know that I'm not going to be using what we just learned very often. I'm really going to be using the second notation here. But it's good to learn it, though. But most everything that I do is going to be using the second method here. It's kind of like a second method. So also, if f of u is differentiable at a point u and g of x is differentiable at x, the composite function, so we talked about the composite function, where we have an inside function g of x, outside function f, it's going to be differentiable at x, and the derivative of the composite function is going to be the derivative of the function f at the inside function times the derivative of that inside function. All right, so it's going to be fewer steps normally is what it's going to end up being. All right, and I think this is what I wrote on your formula sheet too. Okay, so difficulty with the Leibniz notation is that it doesn't state specifically where the derivatives in the chain rule are supposed to be evaluated. So sometimes it's helpful to think about this using the functional notation. So that's what I have here. dy dx is equal to derivative of f at g times the derivative of g. So here in the study tip, I wrote in words, we're going to differentiate the outside. We still have an outside and an inside function. Chain rule is always about outside and inside functions. So we're differentiating the outside function, f is the outside function, at the inside function. So that means we're just going to copy the inside function. We're going to leave it alone. And then we're going to multiply by the inside function. So it's the same thing that we were doing before. It's the exact same thing, but it's going to be kind of fewer steps. We're kind of going to do some of this stuff all in one step. So let's find the derivative of y is equal to 3 plus 2x squared again. So we already did this one. This was the second one we did on the first page. But let's do this using this functional notation. All right, so y is equal to 3 plus 2x squared. So our functional notation, dy dx, I'm going to just copy it up here, says derivative of f, which is the outside, at the inside. So that means we're going to look at the derivative of the outside, and we're just going to copy the inside. Whatever we get there, we're going to multiply it by the derivative of the inside, g prime of x. All right, so we're still looking at y being equal to, or we're still looking at f of g of x, where g is the inside and f is the outside. All right, functional notation, y prime is equal to. All right, so we can see an inside function, 3 plus 2x, and we can see the outside, something being squared. If we're going to take a derivative of the outside, if we want to find f prime, derivative of the outside, this is what we want to find first. Derivative of the outside is going to be 2 something, right? It's going to be 2 times some inside function. So it's going to be 2 times the inside function. The inside function is 3 plus 2x. And now we always have to decrease the exponent by 1. So we're decreasing the 2 by 1, so we're leaving it as a 1. So this is basically as a 1 here. So it's a little bit of a shortcut from what we did before. So we're taking the derivative of the outside, we're bringing that exponent to the front, at the inside, just copying the inside. That's what this notation here means. Then we're going to multiply it by the derivative of the inside, which is 2. And then let's simplify this. So we can multiply the 2 times the 2, and that's going to be 4 times 3 plus 2x. And then we can leave our answer like that. So same answer that we got before. All right. I know it's a little bit different. Each of these methods take a while to get used to. So we have kind of 2 methods now. So let's look at finding the following derivatives. Let's use both methods for finding these derivatives.
So we can actually choose which method?
You can. You can choose. Try them both and see which one you prefer. I will almost always use the second method once we kind of get used to that method. But you can choose whichever one you want. So let's look at this example. Y is equal to tangent of the sine of x. So again, remember, this is not y is equal to tangent of x times sine of x. So be really super careful. If I put this on a test, I could give you both of these problems on a test. Tangent of sine of x and the tangent of x times the sine of x. And you're going to do them in completely different ways. Here you're going to use the product rule. You can't use the chain rule on this one. This one you're going to use the chain rule. You can't use the product rule on this. So completely different answers.
Oh, you know the difference.
So this is a product of 2 things, tangent of x times the sine of x. This is not tangent times sine, because that doesn't make sense. You can't just have a tangent hanging out there with nothing after it. You always have to have something. Yeah, it doesn't have an x. You can't just take a tangent of nothing. This is the tangent of the sine of x. That's what you're taking the tangent of.
That's like 1 angle, 2 angles.
It's, the angle is x, so you're finding whatever that angle is, you're taking the sine of it, and then you're getting a number, and then you're taking the tangent of that. All right, so let's look at this Leibniz notation first of all. So our first method that we just learned. So we got to find our inside function, u, sine of x. We can do du dx. Du dx is cosine of x. And then let's find our outside function, y. Y is tangent of u. So tangent of u, and then we're finding dy du. Derivative of tangent u is so secant squared of u, since u is our variable. All right, then to find dy dx, we're going to put those things together. So dy dx, remember, is just what we get when we multiply these two things, du dx times dy du. So we're multiplying cosine of x times secant squared of x. Not secant squared of x, secant squared of u. And then we got to switch out the u. We have to write u in terms of x. So this is going to be cosine of x times secant squared of sine of x. So I'm not going to write secant squared of x, because there is no secant squared of x. Secant squared of u. So instead of u, I'm going to write sine of x, not secant squared of x. So secant squared of sine of x. I need parentheses around that. All right, and then again, just like that other problem that we did, there's nothing else that you can do. There's nothing to distribute. There's no like terms to combine. That's going to be your answer for that one. All right, let's do this one again. Let's do it using the second method. Let me erase this. So we're going to use the functional notation, and that notation said that dy dx is equal to f prime of g of x times g prime of x. That's our functional notation. That's what we're going to use down here for this second method. So let's do this one again. Dy dx. All right, so f prime, remember f is going to be the outside function. What's the outside function of our original function? Outside function? Tangent. So we have to take the derivative. This is telling us to take the derivative of the outside, derivative of tangent. So derivative of tangent is going to be secant squared. Derivative of tangent is secant squared. We want to take the derivative at g, at the inside function. So I'm just going to copy the inside function. The inside function is sine of x. So I'm just going to copy that. And then I'm going to multiply by derivative of sine. Derivative of sine is cosine of x. And then I'm done. So can you see why I'm going to use the functional notation more often than the Leibniz notation? Leibniz notation is nice, it's very systematic, and it's all laid out for you, and you just kind of put the pieces together, piece by piece. Functional notation, you do everything at one time, so it's definitely much less work. You just have to be careful, like when it says to take the derivative of the outside, derivative of tangent, you're not writing secant squared of x, because it's the secant squared of that inside function, secant squared of the sine of x. You're always copying that inside function, always copying it. G of x, inside function, always appears there. You're just copying that inside function. Questions on that? All right, then what I want you to do is go to the one at the bottom of the page here and the top of the next page. There's two problems, and I want you to try both of those problems both ways, Leibniz notation and functional notation. All right, let's take a look at the first one. So inside function u is square root of x. Du dx, square root of x, derivative of square root of x is 1 over 2 root x. And outside function, y is the sine of u. And dy du, derivative of sine is cosine of u. And then Leibniz notation, we're putting those things together. Dy dx is du dx times dy du. So let's do that. We have 1 over 2 root x times cosine of u, but we can't leave it as u. We have to write this as 1 over 2 root x times the cosine of what? So square root of x. We're just going to replace this u exactly with the square root of x. So make sure that you're not adding anything extra in there. We're just writing this as the square root of x. All right. So that's going to be your answer. And you could write that as one fraction as well. You can just put this cosine in the numerator here to make it look a little nicer. So just write this as cosine of the square root of x. So that's your derivative there. All right, any question on that? Did you guys get that answer? All right, let's look at the functional notation, f prime of g of x times g prime of x. So f prime, so we're looking at this function, looking at the same function, derivative of the outside is sine, so we're looking at cosine of something. So it's the cosine of something. The something is going to be g of x. I'm just going to copy the inside function. Don't do anything to it, just copy it. Inside function is square root of x. So it's going to be the cosine of the square root of x. I'll just put parentheses around that. And then we're going to multiply that by the derivative of the inside. Derivative of the inside, derivative of root x, 1 over 2 root x. So that one that just keeps popping up for us, right?
G prime of x is the inside.
Yes, derivative of the inside, derivative of root x.
First root.
Yes. All right, so you get the same answer either way. So whether you're using Leibniz notation or this functional notation, you're getting the same answer. All right, any question on that one?
Cancel out the x squared over x squared.
No, because you can't just have cosine of something left. It's cosine of something. If there was a root x in front,
It wouldn't be cosine of 1.
no, you can't cancel anything there.
Okay.
If you had a 2 in the front, you could cancel a 2 with a 2, but not when it's inside the function. It's a cosine of the square root of x.
Would you accept either or?
What do you mean? Either or what?
Either way, like cos over cos radical x over 2 radical x, or would you prefer it? Or would you prefer it the times or?
You mean, are you talking about the numerator?
No, you'll accept it like on the test if you leave it cos square root x times 1 divided by 2.
Oh, like this one?
Yeah.
Oh, yeah, that's fine.
Either way.
Yeah, that's fine.
Okay.
All right, let's take a look at C. C, I know we're just out of time, but we can do this real quick. Inside function is 1 plus tangent of x. Derivative of tangent is secant squared. Outside function is the cube root. Cube root is the same thing as u to the 1/3. Take the derivative. We did this one earlier. Derivative is 1 over 3u to the 2/3. And then we're just going to put those two things together just like we did before. We have secant squared of x times this 1 over 3. And instead of u, I'm going to write 1 plus tangent of x. So I'm going to replace that u right away with 1 plus tangent of x. And that's going to be to the 2/3 power. All right, and then that's going to be our answer. We can put that secant squared of x in the numerator again, or just leave it like that.
It's not 1 plus secant squared.
Where would the 1 be? You mean for this one? This part?
So inside, which is u, is 1 plus tangent and then x, and then derivative of 1 plus. Okay, because because the first derivative of 1 is going to be nothing. So.
Correct, yeah. Correct. First, the derivative of 1 is 0. All right, then let's do this same problem using our functional notation. this time. So remember what we're looking at is f prime of g of x times g prime of x. So we have to find f prime. So that's the derivative of the outside. So we're looking at this function right here. Derivative of the outside we know is going to be 1/3 something, and then we're going to decrease the exponent by 1. But we're taking 1/3 of g of x. So g of x is going to be 1 plus tangent of x. And then the exponent is going to be 1/3 minus 3/3, so it's going to be negative 2/3. And then we're going to multiply that by the derivative of the inside, derivative of g of x. So if we look at the inside is 1 plus tangent of x, and we want to multiply that by the derivative of tangent of x, and that's going to be equal to secant squared of x. So we're going to multiply by secant squared of x. And then you can see that we get the exact same answer that we got up above. And we can write this with a positive exponent if we want. We can write this as secant squared of x divided by 3 times 1 plus, oops, this should be a 1. Okay, 1 plus tangent of x to the 2/3 power, since we're moving that into the denominator. But the same answer that we got before. So you can write it like this or like this. Those are the same. All right, then let's go on to part 3 in your lecture notes where we talk about repeated use of the chain rule. So let me get a new page here. And for this one, we're going to find the derivative of sine of the sine of the sine of x. All right. So inside function, we see this sine of x, and we're taking the sine of that, and then whatever we get there, we're taking the sine of that. So again, it's not a product of something. It's not sine times the sine of x. This is something where we need to use the chain rule for. It's the sine of the sine of the sine of x. All right, so let's use our functional notation here. And the functional notation means we're going to first identify inside function and outside function. So we know that the sine is going to be an outside function. And then for inside, for right now, we're going to use this whole thing as our inside function. So remember, we're looking at f prime of g of x times g prime of x when we find this derivative. So y prime is equal to, first we want the derivative of the outside, derivative of this sine. So this one here. Derivative of sine is going to be cosine. And then after we take that derivative, we're just going to write the inside function. So we're going to write, just copy it, sine of the sine of x. So don't change it, just copy it exactly the way that it is. And then we're going to multiply by the derivative, and I'm just going to show that, and then we'll do that. Derivative of the inside, d dx of the sine of x. So I'm just copying that. All right, let's do that derivative. So just copy cosine of the sine of x. Now let's just ignore the stuff to the left. So just ignore this part here. And then let's take the derivative of the second part. So let's just focus on this, taking the derivative of this. Now we have a new inside and a new outside. So let's see if I can erase this. So now for this part, this is going to be an inside, and the sine is going to be the outside. So let's just do that. So let's take the derivative. So again, we're going to use this functional notation. So the derivative of the outside, derivative of sine is cosine. At the inside, so just copy the inside, cosine of the sine of x, times the derivative of the inside. So derivative of sine of x is cosine of x. All right, so then this is going to be equal to, pretty much what we have here, just there's not much that we can do to this. We're not multiplying these things. This is the cosine of the sine of x times the cosine of the sine of x times the cosine of x. And really that's your answer. There's nothing that we can do. You can't distribute anything or get rid of those parentheses. So that's going to be the answer for this one. All right, then let's look at part 4 in your notes. And part 4 in your notes says the chain rule with powers of functions. So let's look at the power chain rule. Well, we're going to look at the power chain rule. Let's look at an example first of all. So let's say that suppose we have this function y is equal to 1 plus x squared to the 10th power. So that's example A in your sheet where it says to find the following derivatives. So if we want to find that derivative and we want to use our functional notation, remember f prime of g of x times g prime of x, so derivative of the outside. So if we're finding y prime, the derivative of the outside, we know we have to bring this 10 to the front, and it's going to be 10 times the inside. The inside is going to be 1 plus x squared. And we know to take the derivative of something to the 10th power, we have to decrease that exponent by 1. So now it's going to be to the 9th power. And then we have to multiply by the derivative of the inside. So the derivative of 1 plus x squared is just going to be 2x. And then that's going to be equal to 20x times 1 plus x squared to the 9th power. And so that's what happens when we have a derivative of something that is a power function. So for our power chain rule says if we're taking the derivative of something to the nth power, we're going to bring that exponent to the front. And then we're just going to copy the u and then decrease the exponent by 1 and then multiply by the derivative of that inside du dx. So that's our power chain rule. So when we use that rule, whether we use this rule or our functional notation, it really means the same thing. So let's look at another example. Let's look at example B. So here we want to find d dx of x to the 4th minus 1 cubed. So using that power chain rule, we know that we can find this derivative by bringing the 3 to the front, just copying the inside, decreasing the exponent by 1, and then multiplying by the derivative of the inside. Derivative of x to the 4th minus 1 is going to be 4x cubed. And then you always want to simplify. We can multiply the 3 times the 4, and that's going to be equal to 12x cubed times x to the 4th minus 1 squared. All right, let's look at example C. So d dx of, oops, let me rewrite that. So this is C. So d dx of sine to the 5th power x. So the important thing for this one is just to realize sine to the 5th power, sine to the 5th power of x is the same thing as the sine of x to the 5th power. So we can use that same power chain rule for this one. When we're taking the derivative, we can bring that 5 to the front and copy the sine function, decrease the exponent by 1, and then multiply by the derivative of the inside. So the derivative of the inside is sine of x. All right, so we're just taking the derivative of the sine of x. So let's do that. And we're going to multiply by cosine of x. And that's going to be your answer then. And then what I want you to see is that this is different than if I asked this question. So if I asked you to find the derivative of the sine of x to the fifth power, that's going to be a different problem, because what this means is we're looking at the derivative of the sine of x to the fifth power. So this problem has an inside function, which is x to the fifth power, and it has an outside function, which is sine. So using what we know from before with our chain rule, the derivative of the outside is going to be the cosine, and we're taking the cosine of the inside, so it's going to be the cosine of x to the fifth power. And we're going to multiply that by the derivative of the inside. Derivative of x to the fifth is going to be 5x to the fourth power. And then that's basically your answer. We can put the 5x to the fourth in the front. Cosine of x to the fifth power. And you can see that we get a very different answer for this one. All right, so for this problem here, we can't bring that exponent to the front like we did before, because it's not the sine of x, that whole thing, to the fifth power like it was over here. This is the sine of x, the whole thing to the fifth power, so we can bring that 5 to the front. Whereas for the second one here, we can't do that same thing. So just be careful with that. And then on the last page, I have some practice problems, and just want you to practice finding the derivative of those problems from A to E. All right, let's go through these problems. So for A, when you are finding the derivative of 1 over x squared plus 1, so the best thing to do is probably to rewrite that as x squared plus 1 to the minus 1 problem. Otherwise, to the minus 1 power. Otherwise, you'd have to use the quotient rule to do that. But we can do it this way if we just rewrite it to the negative 1 power. And then using what we know from that power chain rule, we can bring the exponent to the front and just copy the inside, x squared plus 1, decrease the exponent by 1, minus 2, and then multiply by the derivative of the inside, so 2x. And then you end up getting negative 2x over x squared plus 1 squared. And then for problem B, the derivative of e to the square root of 3x plus 1. So we have an inside function, which is the square root of 3x plus 1, and then we have an outside function, which is e. So we have to take the derivative of e, which we know is going to be e, at the inside function, square root of 1 plus x, and then we have to multiply by the derivative of that inside function. So we have to take the derivative of 3x plus 1 to the 1/2 power, that's square root. But then you see with this part, we have to actually take the chain rule again. So do the chain rule again. Because for this part, this derivative, we also have an inside function, which is 3x plus 1, and an outside function. So let's just copy the e to the square root of 3x plus 1. Let's not do anything with that. Now let's focus on the second derivative. So we can use that power chain rule again, bring the 1/2 to the front, keep the 3x plus 1, decrease the exponent by 1, so we have a negative 1/2. And we have to multiply by the derivative of the inside still, 3x plus 1. That derivative is just 3, so we just copy everything that we had in the previous step and add this 3 here. And then we can simplify that, get rid of that negative exponent, and just write it as one quotient, and you end up with this answer here. So that's what you should have gotten for B. All right, so let's take a look at C. This one I haven't finished yet, so we can do this together. So x over the square root of 7 minus 3x. And again, it might be easier to rewrite it as x times 7 minus 3x to the negative 1/2. And let's take this derivative. So in order to do that, we now have a product of two things. We have x times 7 minus 3x to the minus 1/2. So using our product rule says we have the first thing times the derivative of the second. So we're looking at this as being our second function. So we're going to take the derivative of that. Using our power chain rule, that's the negative 1/2, bring that to the front. Just copy the inside. Decrease the exponent by 1. So negative 1/2 minus 2/2 is negative 3/2. So first times the derivative of the second plus the second, so just copy the second function, times the derivative of the first. Derivative of x is just going to be 1. All right, then we can simplify this a little bit. So if we want to get rid of the negative exponent, we can leave, first times the derivative of the second. I forgot when we were taking this derivative right here. When we were taking this derivative, we brought the negative 1/2 to the front, decreased the exponent by 1, and we have to multiply by the derivative of the inside. So we still have to multiply this thing by negative 3. So we need to put that in there. And then we have a negative 1/2 and a negative 3. That's a positive. And we have this x times the 3. So we have 3x in the numerator. And in the denominator, we have 2 times 7 minus 3x. And then the exponent becomes positive when we move it to the denominator. And then this is going to be plus 1 over this 7 minus 3x. Oh, why did I put a 3 here? This should be a 2, because we decreased negative 1/2 by 1. We have minus 1/2 minus 2/2 minus 1. So yeah, that should be a negative 3/2 here. So negative 3/2. And then we can put that in the denominator, 7 minus 3x to the 3/2 power. All right, and then we can just leave that like that. We could do the addition and combine those things, or we can just leave it like that. All right, I need to fix that second part because I was thinking we were taking the derivative of this part, but when we're using the product rule, we do the first times the derivative of the second plus the second. So I had it right the first time. We just are copying that second function, 7 minus 3x to the minus 1/2 times the derivative of the first, which is 1. So I'm just going to change this to the 1/2 power down here. All right, and that's going to be our answer. So we'll leave it like that. All right, let's do, so that's C. So let's do E then, or D. So D is y is equal to 3x times 2x squared plus 1 to the 4th power. So again, this is going to be another product rule, where we're going to use the chain rule. So product rule says we're going to take the first thing, which is 3x, times the derivative of the second, so bring the exponent to the front, copy the inside, decrease the exponent by 1, and then we have to multiply by the derivative of the inside. Remember, this is our inside function, so we're going to multiply that by 4x. So product rule. Then we're going to write the second thing, 2x squared plus 1 to the 4th power times the derivative of the first, so times 3. And then we'll see if we can simplify anything. We can factor out common factor here. 3 is a common factor for each one of these terms, and 2x plus 1 to the 3rd power is going to be a common factor too. So we can factor that out. So this is equal to 3 times 2x squared plus 1 cubed. So if you can factor this at the end, go ahead and do that. And then let's take a look at what we have left. We have one see, we have a 4 here. We have 4 times 4, so that's 16, and then we have this x times this x, so that's x squared. And then we have 2x plus 4 that's left over here. On this side, we have just one of the 2x plus 1's left, plus 2x plus 1. And then this is the same thing as 3. So all factors are going to be 2x squared plus 1 cubed times, this should be 2x squared. So 16x squared plus 2x squared is going to be 18x squared plus 1. And that's going to be your answer, completely factored for that one. And then we have one more problem. So let's write that one down. So so hopefully you tried this one. Y is y is equal to x squared plus 1 to the third power times x cubed plus 2 to the sixth power. Again, product rule. So product rule says the first thing, we're just going to copy it, x squared plus 1 cubed, times the derivative of the second, so we're going to bring the exponent to the front, copy the inside, decrease the exponent by 1, and then multiply by the derivative of the inside, so 3x squared. So that's the first part of the product rule, the first times the derivative of the second, plus the second thing, so we're going to copy x cubed plus 2 to the sixth power, times the derivative of the first thing. So 3 times x squared plus 1 to the second power times the derivative of the inside, so times that 2x. And then we're going to see if there's anything that we can factor. So let's look for common factors here. So x squared plus 1 is going to be a common factor. We have an x squared plus 1 to the third power, x squared plus 1 to the second power there. And we have a 6 here that we can factor out. We have a 6 here, and we have an x here, and we can use factor out one of these x's here. So we can factor, and then we have x. I wrote this wrong in the beginning. This should be x squared plus 2. So let's fix that, x squared plus 2. So first times the derivative of the second, so we have to copy x squared. And then we're multiplying by, let's see, first times the derivative of the second, derivative of the inside, this should be 2x here, times 2x. All right, so let's fix that. Plus the second, x squared plus 2 times the derivative of the first. That one should be fine. All right, so let's factor out a greatest common factor. So we still have a 6x that we can factor out. And we also have x squared plus 1 in both of those terms, x squared plus 1. And the second power is going to be the smallest one. And then we have x squared plus 2. And then that's going to be to the fifth power. That's going to be the smallest power. All right, then what we have left for the first term after we take away that 6x is going to be a 2. And we have x squared plus 1, the first power. And that's going to be it for the first term. And then for the second term, looking at all of this stuff here, what we have left over, we have the 6x covered, x squared plus 1 squared is covered, and then we have one of the x squared plus 2's left, plus x squared plus 2. All right, so let's completely factor this. So we have 6x times x squared plus 1 squared times x squared plus 2 to the fifth power times, and let's combine like terms over here. If I distribute that 2, I have 2x squared plus 1x squared, that's 3x squared. If I distribute the 2 here, I have a 2 plus a 2 over there, so that's going to be plus 4. And this then is going to be your final answer. That's going to be completely factored for this one. And that finishes section 3.6.